Hello, everyone, and welcome to phyloseminar.org. The current theme is Variational Bayes Phylogenetic Inference, and this is Talk 2 in a series of 3 talks on that topic. Please use the YouTube live comment box to ask questions or tweet at phyloseminar. Today's speaker is Cheng. Cheng got his undergraduate from Peking University, then his PhD from UC Irvine under Hongke Zhao and Babak Shoa, where he worked on scalable Hamiltonian Monte Carlo algorithms. He then spent 2.5 years in my group where he did the work he will talk about today, along with several other interesting and technically difficult projects. He is now an assistant professor in the Department of Probability and Statistics at Peking University. Welcome, Cheng, and thanks for speaking to us today.
Well, welcome everyone. And first, thank Eric for the invitation and the nice introduction of me. So today, I'm going to talk about variational Bayesian phylogenetic inference, which is some of our recent works on this exciting field of Bayesian phylogenetic inference. So let's get started. So first, just a quick review of phylogenetic inference, which I assume that many of you are very familiar with. So the goal of phylogenetic inference is try to reconstruct the evolution history of some species of interest from their molecular sequence data, like DNA, RNA, or protein sequences. So here is a typical example of what a phylogenetic tree or the evolution history look like. Usually, it will be a bifurcating tree topology with the tip nodes representing this species of interest. And this will be the data we have. So we have species and their corresponding sequence data that are aligned. So each of the column actually corresponds to the observations for size. Okay, so this kind of models have a lot of modern applications, like in biological and medical applications. For example, they have been used to predict the evolution of influenza viruses. That allows us to design some policies to control the spreading of some disease, and also it helps to refine our vaccine design process. So here is a concrete example on B-cell evolution process. I'm not quite familiar or an expert on this field, but I'll try my best to give you some big picture of this process. And this is actually what happens inside of you. And the following graph I steal from some of Eric's recent slides. Okay, so this orange ball represents the B cell that generates antibodies, try to bind with antigens, and this antibody will then work to help us fight against those viruses. Okay, and it has to undergo an evolution process to become mature. So how does it work? First, it tries to generate antibodies that bind as many antigens as possible on the FTCs, right? And after that, it will be selected by those helper T cell according to their how many antigens they bind. So actually, this is a reflection of the level of affinity. Okay, and this is a highly competitive selection process. And after that, only this B cells that are selected by this helper T cell will survive. Okay, and then they give birth to the next generation, which is it's a hypermutation process. So it generates a lot of children which enters some of this high level affinity it has, and also it promotes some mutation that will increase the diversity of the antibody it generates. And then this next generation will undergo the same process. They fight with each other to grab as many as, or to bind as many as antigens they can, and then got selected by this helper T cell according to their affinity level. Okay, so after several generations, only those B cells that can generate a high level affinity, has a high level affinity, will survive, and then it becomes a mature B cell that can work in our immune system. Okay, but this whole process happened at a very large population size and in a very short amount of time. So only God can see the entire evolution process. And what we observe in practice is only those tip nodes, those mature B cells. So what we want to infer now is just the entire evolution process, because this contains useful information that could help us in our vaccine design. Okay. So hopefully now you agree with me that this reconstruction of the evolution process or phylogenetic tree is very important. But how can we do that? Actually, there are many methods like distance matrix methods and parsimony-based methods like maximum parsimony approach. But today we're going to focus on a probabilistic formulation that allows us to do this fancy Bayesian stuff that can provide estimates that are robust to the change of the data we have. Okay, so the core of a probabilistic approach is actually a model that describes the generative process of the data. So here for a phylogenetic model, the generative process contains two components. One is the bifurcating tree topology, tau, which is the phylogenetic tree topology. And also we need a continuous component, which is the evolution time from the parent to the child. The tree topology actually describes the global picture of how this evolution happens in a large scale. But we still need another component, which is a model to describe the transition from the parent to the child. We call it evolution model. Usually we'll use a continuous time Markov chain to do that, which takes in a continuous parameter. It's non-linked to parameter, the evolution time on the branch that reflects the amount of evolution, and then output the transition probability from the parent to the child. If we use the DNA sequence, then there will be a 4x4 matrix from ATGC to ATGC. Okay, and now with these conditional probabilities, we'll be able to compute the complete data likelihood, assuming that we have the observation on the tips, but also on the ancestor nodes. So we can multiply those conditional probability together by assuming the corresponding conditional independence induced by the tree topology. We have the observation on the tips, so we have to do the marginalization to sum out this ancestor nodes. This seems to be a very costly process because, see, for this example, each of these hidden nodes or ancestor nodes will have 4 possibilities. So combine them together, it will be 4 to the third computation. And if we have n sequences, then the computation cost would be 4 to the n-1. But fortunately, this is a tree-shaped graph, so we can rearrange the summation order smartly to reduce that computation to be linear. The corresponding algorithm is called the pruning algorithm in phylogenetic community, introduced by Falsenstein, but it's also known as sum product message passing or variable elimination in probabilistic graphic models. But anyway, now we have a very nice and efficient algorithm to compute the likelihood in linear time. And then we can assume that all these observations are independent. So we can multiply all the side observations together to get the full data likely function. Now with the appropriate priors, we'll be able to compute the posterior up to a constant. And from there, we can choose our favorite Bayesian inference methods like MCMC. And now for Bayesian phylogenetic inference, the mainstream methods is really the Markov and Monte Carlo methods, or more specifically, random walk MCMC, where people just use sample random perturbation, like nearest neighborhood interchange, to generate new states. You can do that for the tree topology, and also you can random perturb the associated branches to get a new state for the branch as well. This line of research has been pioneered by a lot of like Yang, Mao, and Houston, Beck, and Ronquist near the end of last century. And the random walk-based MCMC has been implemented in many like phylogenetic computing softwares like Beast and Mr. Bayes. But there are also many challenges for this MCMC methods. The first thing is the search space or the parameter space is super large. So think about how many tree topology we have to explore to get the posterior. Like you can compute it for the total number of unrooted tree of n taxa will be 2n-5, double factorial. So this is a number explodes combinatorially. It's super large. If you can try that for n equal to 50 or 100, you will get a number that is already larger than the number of total all atoms in the universe. Okay, and to make it even worse, we have a continuous component, the branch lenses, and these two parameters just intertwine with each other. That means if we make large tree modifications, we'll have a relatively low acceptance rate. So that makes it even harder to scale to data sets with many sequences, because we really rely on this large tree modifications to explore the tree topology efficiently. Okay, so how can we do? What can we do to improve the Bayesian phylogenetic inference masses? And really, the bottleneck is about exploration in the tree topology space. So in our recent work, we developed this variational Bayesian phylogenetic inference masses, which we have a component that allows us to explore this tree topology space more efficiently. And this is actually based on some of our recent works on designing a powerful graphic model that can learn the distribution over the tree topology space. But before that, let's just give a quick review of variational inference. Okay, so what is variational inference? Well, unlike MCMC that samples from the posterior directly, variational inference tries to find the best candidate from a family of tractable distributions that minimizes some distance to the target posterior distribution. So here we have denoted this family of distributions Q. So that's usually called the variational family of distribution in VI. That's the first thing we have to choose. And after that, we can fit this variational parameter phi to minimize this distance, usually the KL divergence, to the exact posterior. Okay, but unfortunately, the KL itself is intractable because it still involves the exact posterior. So in practice, people often turn to an alternative approach, that is to maximize the evidence lower bound instead. So this is given in the equation above. We can see now this elbow only requires the joint probability of the px theta. So the model evidence part, or the normalizing constant part, has been moved to the right-hand side. That is the model evidence that we lower bounds. Okay, so the elbow is a lower bound. As we can see here, the elbow is a lower bound on log px, and also we can easily show that maximizing this elbow is equivalent to minimizing the KL divergence, because the gap between this elbow and log px is just exactly the KL divergence. And the elbow actually strikes a balance between two terms, as we can see here. The first term is usually known as the energy term, that is expectation of log px theta with respect to q theta. So actually, it encouraged Q to focus the probability mass where the model poses high probability. And the second term is an entropy term. So actually, it encouraged Q to be diffuse. So combine them together, then we have a strategy. The elbow will push the Q theta to approximate the real posterior. So now, as an optimization approach, VI tends to be faster than MCMC because you don't have to run many iterations to gather samples. As long as you can arrive at a good point estimate, then VI will succeed. And it's also much easier to scale to a large data set because we can naturally combine it with stochastic gradient ascent. Now probably you have a big picture about how VI works, and the two essential ingredients of VI is, first, we have to find an approximating distribution, a family of flexible approximating distributions, and second, we have to find a metric, a distance between distributions. Okay, so if we want to apply this idea to phylogenetic inference, first we have to find the distribution over the phylogenetic parameters, which is a little bit complicated because we have tree topology plus the branch lengths and possibly some other continuous parameters as well. So how are we going to do that? Unfortunately, from our previous project, we have a very nice probabilistic graphic model that can really learn a nice distribution over tree topologies. So let's introduce it first. This graphic model we call the Substrate Bayesian networks. So how are we going to link a probabilistic graphic model with a distribution over tree topologies? Let's do it with a vivid example here. And I will show that how to encode the tree topologies or tree structures via Bayesian networks. So here are two trees on the right-hand side. Okay, so if we follow the splitting process of that, or the evolution process of the tree, we'll see that at the root node, it first splits into two parts, A, B, C, and D. This is a bipartition, or you can call it a root split or subsplit. And D is a syncline clade, so it cannot be split anymore, but clade ABC will continue to split into A and BC on this tree, right? And then finally, BC splits into B and C. So actually, a tree can be represented as a series of splitting process, or a series of subsplit. Okay, and we can do the same thing for the bottom tree. But you may realize that if we do that, then this representation is not unique, or the pattern of the representation is not unique, because the graph is changing, right? So now if we further allow this second clade to split until the depth of 3, because now we have 4 taxa. If we have n taxa, then that process will continue to n-1 depth. Okay, and with this faking splits, we'll complete those graphs to make it a unified framework, right? Which is just a full and complete binary tree.
Maybe Cheng, can you just repeat the definition of subsplit one more time, just to make sure that people understand what's going on?
The subsplit actually is quite similar to a split, but it's based on the clade. So if we have a clade ABC, any kind of bipartition of this clade will be called a subsplit, and we have an order on that because now if we choose an alphabet order A, B, C, D, so we put A first and B, C on the bottom. So it's an ordered bipartition. That's a subsplit.
Cool, thanks.
Okay, so now you realize that this is nothing but a Bayesian network, right? Where the nodes just take on the subsplit values. And each tree can be uniquely represented as a series or the sequence of these subsplits. So that corresponds to assignments of this Bayesian network. And we call this Bayesian network substrate Bayesian networks. And with that, if we have some parameters for this conditional probability tables, these are the natural parameters for a Bayesian network, then it implicitly defines a distribution over the entire tree topology space. And we can evaluate the probability of those trees by multiplying all this associated conditional probability together. So that is given in the following formula. Okay, and that is for rooted tree. And we can do the same thing for unrooted tree, just by realizing a very subtle connection between unrooted tree and a rooted tree. Because for each of the unrooted tree, we can represent it as a collection of rooted tree by just rooting at all these possible edges, right? So in this way, each of the unrooted tree can be represented as a collection of rooted tree. And for each of this rooted tree, we can compute the probability as before. So in the end, we can sum all this probability together to get a probability estimate of this unrooted tree. So it's like that. Now we are using a Bayesian network with the root node missing, right? So the root node can take any compatible root subsplit of this unrooted tree. Okay, it's easy to verify that in this way, we still give a valid probability distribution over the unrooted tree space. So now that SBN can learn distributions of trees, we can use that to learn a probability distribution estimates based on a collection of trees, and assume that each tree had been already represented as a series of subsplits. That's our input data. For a rooted tree, this process can be done very straightforward using this maximum likelihood estimation. And it turned out that those conditional probability estimates will be just the relative frequency. It's very intuitive because this SBN-induced distributions are naturally factorizable. Okay. For unrooted trees, things got a little bit complicated, but still, we can view this root node as a missing data. So we can use EM for learning, where in the E step, we just compute this conditional probability of this missing root node as 1, given the current parameter estimates. And then we use that to compute the expected complete data log likelihood, which turned out to have a similar form of this likelihood, log likelihood. So the maximization is kind of in the same way of maximum likelihood estimation we have for the rooted tree. So it's quite convenient. So now we can run EM for several iterations until it converges. So let's see how it works on real data set. So this is the first experiments we have done on DS1, which is the RNA data set that has been used as a benchmark data set for MCMC performance comparisons. So we use that as an example and we compare to conditional Clay distribution, which is a previous method introduced by Larget in 2013, and our SBN-based methods using EM. And we see that from the left and middle plot, SBN-based methods significantly reduce the bias, both for the high probability trees and also this low probability trees. And we also compare the KL divergence from different methods to the ground truth we obtained by running MCMC for an extremely long time iteration. And we can see that the CCD is not that data efficient, because when we get more samples, it's just stop improve, or the improvement is really subtle, it's really marginal. But for all the other competitive methods like SBN and the sample relative frequency, which is the method we use to get the ground truth, they keep improve as more samples are available. Okay, so what I want to mention here is really for this weak data regime, because this is really something happening in practice, because collecting this MCMC sample is super costly. And we can see that in this weak data regime, our SBN-based estimates are much better than all the other methods. Okay. And we also apply our methods to a wide range of datasets from DS1 to DS8. Those are the datasets that have been used to benchmark MCMC performances before. So we can see, other than this very simple posterior on DS2 that only has 7 unique trees in the posterior samples, our SBN methods significantly outperform the other methods. And even if we only look at this absolute value of these approximation accurate in terms of KL divergence, SBN also performed quite well. So that actually is an indicator for us, which showed that SBN maybe are flexible enough to provide accurate approximation to real data posteriors. So why not just use the SBN to learn this distribution directly instead of requiring MCMC methods, right? And we have said that before. In a variational inference approach, the first component is to design an approximating distribution. And now we have a nice approximating distribution over the tree topology already. So what we have to do next is just to find a nice approximation for the branch lengths. And then we can combine together to use that as our approximating distribution. So I will describe about the branch length distribution in more specifically in the next slide. And once we have this approximating distribution, then we have to choose a training objective. So instead of using the standard elbow, now we're going to use multi-sample elbow. And there are 2 main reasons for this. The first one is we really have a very nice, very hard space to explore, the trace topology space. So we want to use multi-samples to increase the exploration ability of our method. The second thing is the tree topology is really a discrete and structured object. So the gradient computation is not that efficient for a single sample elbow, but for multi-sample elbow, we have nice gradient estimators, as I will describe next. So now with this approximating distribution and this training objective, we can just use stochastic gradient ascent to maximize this elbow. And to get this stochastic gradient estimators for phi and psi, we'll use VMCO and RWS for phi. This is a latent variable for the tree topology. And we'll use the reposition trick for psi, because it's for the continuous branch length parameters. Okay, so now let's talk about the structure parameterization for our variational distributions. For SBNs, the parameters are really those conditional probability tables. So we have a nice parameterization using the softmax function, which is quite straightforward. For the branch length, we're going to use normal distribution. So it's really a very coarse approximation, because we assume that the branches are independent on a given tree topology. And the naive parameterization then requires us to specify the mean and variance for each of the branches on each tree topology. And if the target distribution or the high probability domain of the true posterior contains a lot of tree topologies, this naive parameterization will cost us a lot of parameters. So that is not efficient. Another reason is that if we use this to, when we train these parameters, it's not that the training process could be slow, because we can only update the corresponding parameters for a tree topology by sampling it, right? We have no chance to update the parameters when we don't sample that tree topology. Okay, so in order to improve or reduce the number of parameters and also improve the speed of training, we're going to borrow some ideas from the VI community, where they just use so-called amortization techniques. That is, they don't specify the parameters for the specific parameters in the model. Instead, they specify parameters for a shared objects. And in this case, we can go and find some shared, local structures among tree topologies, and then we can assign parameters to those shared objectives. The first thing we come up with is just a simple split parameterization. That is, we can assign parameters to this split that correspond that can be used to represent the branches where the branches corresponds to, because each of the branch naturally corresponds to a split. By you can cut this branch and it naturally divides the tree into two parts, and that is a split. Okay. And the interesting thing is the split will be shared by a lot of tree topologies, right? Even though they have different shapes. And this simple split-based parameterization actually works quite well, but it has a potential drawback. That is, if you have two different tree topology, and as long as those two branches on those two different tree topology corresponds to the same split, we have to use the same approximating distribution for it, which might not it's not likely to happen in real cases, because the distribution actually depends on the context of the entire tree topology structure. So to improve this approximation, we'd like to inject more local information about trees into our parameterization. And that's why we come up with this primary subsplit pair parameterization. So in addition to this split features, we just add some local features of the tree to the branch. Okay. And this is what we call the primary subsplit pair, where it is the right next subsplit happening after this root subsplit on this edge E. Because you can think of, okay, if we choose a root here for this right on the branch E, then it has a natural split, W and Z. And after that, we have the split on the W side, splits into W1 and W2. We call this right next split, W1, W2, given W and Z as a primary subsplit pair. And if the same thing happens on the Z side, then we get another primary subsplit pair, Z1, Z2, given W and Z. So now we assign additional parameters to this primary subsplit pairs and add them up as our parameterization or final parameterization. Okay. And as you will see later, with these additional features from the tree or tree-specific features, this will improve our approximating quality, and also it will ease the entire training process, because it's more flexible across different tree topologies. Next thing is about the stochastic gradient estimators we need to train our parameters. So for the SBM parameter phi, we use VMCO and RWS, because those are control variate-based gradient estimators that works for general latent parameters. So now for the tree topology is a discrete parameter, so that's the only stochastic gradient estimator works for those kind of parameters. For VMCO, it's introduced by Ming and Rizenda in 2016. And the nice thing is VMCO actually utilizes the continuity of the learning signal, and then it constructs a control variate using the other samples, and that will significantly reduce the magnitude of the learning signal, and therefore we have a stochastic gradient estimate with relatively small variance. And for RWS, it's actually based on an alternative training objective. So it's a reverse KL divergence. And the estimate is based on a self-normalizing importance sampling procedure. Okay. And the interesting thing is for RWS actually is based on another training objective. But I guess why it works is because when our approximating distribution becomes more and more accurate, then those two training objectives, the reverse KL and the KL, becomes very similar to each other. And for the branch length parameters, because we use log normal, so it has a natural representation transformation, which is given here. So now with that, we can use the representation trick directly. And people have shown empirically that if representation trick works, then that will give the lowest, the unbiased gradient estimator with the lowest variance. Okay, so now we have completed the whole procedure of VBGPI. So I'll give a global instruction of what I call this VBGPI pipeline. So now start from our tree topology approximating distribution, Q phi tau, it could be an SBN. Then we can sample from this distribution by using a so-called ancestor sampling procedure. So this is a standard sampling procedure for any Bayesian networks. For example, we can start from the root to sample the root split according to the distributions. And then given that root node, we can sample from its conditional probability tables to get S2 and S3. And we can keep doing that until we get all the samples for this nodes on this Bayesian network. Notice that now, if we have a single clade, we can stop sampling from that because we really want to get is the tree topology, right? It's not a unique representation now. Okay, so this is just the inverse process that we get a connection between the Bayesian network and the unrooted tree topology. And if you want to sample from the rooted tree, unrooted tree, then you can just sample a rooted tree and then unroot it. So now with that, we'll get a collection of tree topologies, right? And then conditional on this tree topology, we can sample its corresponding branch length distributions. And that will give us a collection of complete tree, phylogenetic trees. And use that, we'll be able to compute an estimate of the lower bound and also the gradient, the stochastic gradient of these parameters. And use this stochastic gradient, we'll be able to update our parameters. And we can continue this loop until convergence. And that's the VBGPI algorithm. Now let's see how it performs. The first experiments we have done is on synthetic data, where we use the unrooted phylogenetic tree space with 8 leaves as our tree space, and that includes 10,395 unique trees in total. And the target distribution is just a random sample from the symmetric Dirichlet distribution with a concentration parameter beta equal to 0.08. And notice that here, this target distribution is a valid distribution. So the model evidence is actually log 1, which is equal to 0. So the left plot actually shows the different VBGPI approach. The evidence lower bound given by different VBGPI approach, where we use different stochastic gradient estimators, VMCO and RWS, and also different number of samples in the multi-sample elbow training objective. We see that all these elbows approach 0 quite quickly. That means SBN actually can provide really flexible approximations. And also, if we increase the number of samples in the multi-sample elbow training objective, the performance improves, both in terms of the lower bound and also the KL divergence. So that means actually using more samples is helpful for VBGPI training. And the right plot actually shows the variational approximation given by VMCO and RWS compared to the ground truth. And we can see that their performance is quite similar. There's only a subtle difference is here. Maybe it's not that recognizable. That is, the VMCO actually slightly underestimates the probability of trees in the high density domain, while RWS actually underestimates the probability of trees in the less likely tree space. Okay, this is probably a result of the training objective. And the next experiments is on real data, DS1, as RN dataset we have mentioned before. So here we try different stochastic gradient estimators, VMCO and RWS with different number of training objectives, number of samples in training objective, multi-sample allowable as before. We see that actually now more samples actually encourage exploration, and then in the end we'll get a better approximation as we observed in the simulation data as well. And if we use PSP, which is another more flexible branch length parameterization, the left plot is actually for the split parameterization. So the mid plot is for the PSP parameterization, which is more flexible across different tree topologies. We can see that actually the training curve is more smooth. So that means using PSP is likely to ease the training. And also in the end, we'll have an improvement for the overall approximation. So that means if we have more flexible branch length approximations, then across different tree topologies, that will ease our training and improve the approximation. And we'll also compare to MCMC as a benchmark, here shown in the green dashed line. So we can see that even though our method VBGPI is kind of slower than MCMC, but as long as it can learn a reasonable approximation of the tree topologies, then it begins to accelerate and quickly surpass MCMC and arrive at really good approximations with less computation. Okay, and the reason is because in the end we'll get more and more efficient tree space exploration induced by SBN based distribution, and also the branch length update by our structured branch length parameterizations. And all this VBGPI based variational approximation in the end will be used to can be used to estimate the marginal likelihood per tree topology via importance sampling. So here we compare to one of the state-of-the-art methods, the generalized stepping stone, for the 95 credible intervals of the posterior in DS1. We see that those two methods provide similar estimations of the marginal likelihood, and VBGPI's estimates really have a small variance in general. Okay, and we can do the same thing for the entire marginal likelihood, which means that we can also integrate out the tree topology, right? And for that, we compare to a stepping stone method, which is one of the state-of-the-art methods for doing this, and we can use this marginal likelihood for model selection, for example. So we test our methods across different dataset from DS1 to DS8, which we have seen before, and we use the VMCO for training with and without PSP. We see that actually the performance is quite competitive to the state-of-the-art methods SS, but our results is based on just 1,000 samples, while SS requires 100,000 samples that has been obtained from an even larger number of iterations. So SS is a very slow method, but with that, with only 1,000 samples, our results is already competitive and can provide more stable estimates than SS in most cases. And also, we realized that using PSP, now we'll be able to provide the same quality of approximation with less samples in the training objective. So PSP actually reduced the demand for large samples that reduce the computation while maintaining the approximation accuracy. Okay, so let's just summarize a little bit in the end. So we have introduced VBGPI, which is a general variational framework for Bayesian phylogenetic inference. And VBGPI allows efficient learning on both tree topologies and branch lengths that provides competitive performance to MCMC while requiring much less computation. And all these variational approximations obtained from VBGPI can be used for further statistical analysis, like marginal likelihood estimation, the importance sampling. That could be quite useful for model selection, for example. And there are many straightforward extensions, including more flexible branch length distributions. Remember that we only use very simple log normal or diagonal log normal distributions, and there could be many other possibilities for that. And we can also try to extend VBGPI to more general models that includes more like substitution rate parameters, and also including this time tree models. And also, we can use SBNs to design adaptive transition kernels in MC approaches, and using this structured parameterization of the branch lenses as well. So that's it. And those are the two related papers of my talk. If you're interested, you can find more details in there. And thanks for your time.
All right, thanks, Cheng. So we'll take any questions that people have. Like I say, you can either, I'm looking at both the YouTube comments channel and Twitter. I guess I can just sort of ask, so I mean, one thing that you didn't quite cover there concerns the support of the SBNs, which is sort of a technical thing, but important as well. Or maybe you did and I didn't notice it?
Yeah, I didn't cover that. Yeah, that's true. Because in addition, if we want to specify a parameterization of this SBNs, we really need to get a support of this likely subsplit pairs, right, from the parent to the child. So in our paper, we actually find out we can get a reasonable estimate of this support by using some fast bootstrapping approach. And also you can run some initial MCMC runs to get a collection of nice trees. It does not have to be high quality posterior samples, as long as you can cover all those parent and children subsplit pairs from this high posterior trees, then it will do the job. But I think that we can find more efficient way to get that support.
Yeah, I mean, I think, and something that I've been thinking a little bit about is how do we go about expanding that support? So if we have some sort of heuristic method for coming up with an approximate support, how can we?
Yeah, that's true, and I've been thinking about it for quite a while. Ever starting, I'm thinking about this project. Actually, there could be something like we can, dynamically change the support by, random samples, adding some random predation to trees, right? And then you can test whether this is a good tree or not, and decide to add it to the support or not. So that could be something that we can do in the future.
So, I mean, I guess I also want to mention we should also give credit to Sebastian Hunna and Alexei Drummond, who sort of started the whole thing. I mean, it sort of came through, like you mentioned, Larget's work, which was also, I mean, I think it might be worth just sort of going back, since people might be more familiar with his work, just going back to some of the definitions of the subsplit base network and sort of saying, how does the Larget's CCD fit into this same framework? Because it kind of does. It's just sort of a different conditional distribution. Yeah.
Yeah, it's not conditional on the.
It's not conditional. An unconditional distribution.
Yeah, conditional on the clade.
Yeah.
So we have a subtle difference here. Yeah. So for example, in clades, in CCD actually it only contains on the clade. Like it's not conditional on A, B, C, and D. This pattern. It's just A, B, C, and here it's not conditional on A and B, C. This splitting pattern. It's just conditional on B and C. So it's because we have included this sister clade here, so we have more information that can flow into the other part. That actually gives us extra flexibility for our approximation. And we can show that actually if you use CCD, then the probability estimate for the rooting tree does not depend on the rooting position, but in our case it depends. So that actually allows us to use more parameterization power to get better approximation. Otherwise, even though you give different parameters for the rooting position, it will not change the probability estimates. So that's one of the limitations for CCD. But where is it? Oh, yes. So I didn't give the formulation of or a general framework for CCD, but it's actually quite similar to our case here. The only difference now, the node just takes this clade values. Yeah.
So, I mean, besides some of the other things that you talked about, like future directions, I mean, do you think that the VBGPI is held up by just the framework of the standard Kell divergence variational inference setup? I mean, is it worth exploring other divergences? Or do you think that we need to focus our energy on other things?
I think this is a very interesting question. I haven't thought about that yet, because there could be some other possibilities for, for VI. Actually, we have many opportunities to design the training objective. Multi-sample elbow is definitely one option, but there could be many other things. Like we can try something like F divergence, or so. The really challenging part is for the exploration, I think. So we have to explore this tree topology space to find our best approximation. So anything that we can use to design a training objective that encourages this exploration will be helpful. But this is really a very general thing to think about. So I think maybe there could be some opportunity to design more robust training objective other than this multi-sample based elbow. A adaptive F divergence maybe could do the job, or there could be many other things.
So this just goes to show how little I know about this area, but I didn't actually know that the reparameterization trick can be shown to have the lowest variance. Use it.
So I think there might be some theoretical work that prove that it's the best one that provides the lowest variance, but the people have validated in many applications. So there are many empirical success or empirical evidence that among all this existing stochastic gradient estimators, if you can use reparameterization trick, that always provides the best.
Okay, so that's not a theorem.
That's not a theorem. Yeah.
Okay. Somehow I thought I heard that you thought that maybe it was a theorem. One sort of thing that I don't know if we really talked about, but that I think is sort of interesting to think about now is how, with respect to what you were talking about with the stepping stone and marginal likelihood estimation. So one of the main applications of marginal likelihood estimation is model comparison, and it just seems like this provides a really nice framework for doing that. Like, given that models probably don't differ all that much between one another, like with classical MCMC based marginal likelihood methods, you have to sort of start your chain again and run it to completion with all the different models. But it seems like with variational inference, you can just sort of take a few gradient steps, which would probably be plenty to update it.
That's true.
Just because I mean it's not going to change the topology distribution that much, and that's sort of the hardest thing to get.
That's true. Yeah, and hopefully that's true for the real posterior. If you change the model a little bit, then the posterior not just got shifted entirely.
Yeah, then, I don't think the tree distribution changes crazily. I mean, I certainly like you know the model parameters are a completely different thing, but
yeah, and if we can add some other exploration behaviors to the SPN support, maybe we can better capture this kind of shift. Yeah, so that's really one advantage for this variational approach, because we already get a nice approximation of it. So we only have to do a little bit modification, running some extra stochastic gradient descent steps to adapt to a new posterior.
Okay, well, I don't see any questions, so I will close here. I actually have to run myself, but thank you very much, Cheng, and we'll see folks in a little bit for the last talk for the VBGPI series. Thank you.
Thanks everyone.